French? Okay. So I will talk about graph embedding, and we'll do some physics on that. Okay. So this is a joint work with Alexandre here and Marc. And so, as you know, many types of data can be represented by graphs. So these are a couple of examples. You may look at flights between airports, like the graph of Amazon products, actors of Wikipedia, and so on. So here the links may be explicit, like in flights connecting airports, or the links in Wikipedia, or they may be implicit in Amazon products. For instance, this is a graph of co-purchase, so products that have been bought together. You put a link between them, or the actors. You put a link if they have acted in the same movie, for instance. Okay. And a key feature of real graphs is that they are sparse. Typically, it's a density, so the fraction of edge compared to the fraction of the fraction of edge to the number of node pairs. Okay. And so you'd like to have some denser representation of this graph, okay, for many situations. And so this is the problem of graph embedding. Okay, so you'd like to have a representation of each node of the graph by a vector of low dimension. Okay, so I will try that. So, for instance, this node will be mapped to this point. So this is a vector, and so this one will be there, and so on. And what you expect is that a good embedding would be an embedding where nodes that are close in terms of in the graph, so they are neighbors, or they have many common neighbors, are close for the Euclidean distance in the embedding space. Okay. And this is useful for many learning tasks. I mean, this is in many cases is a preliminary step, after which you can apply your favorite learning technique. Like you may do unsupervised learning, like ranking nodes, clustering nodes, applying k-means, for instance, or you may apply semi-supervised learning. In the case you have the labels of some nodes and you like to learn the labels of other nodes, it's easy to apply classical techniques in this vectorial space. Or active learning, like you like to focus on the ambiguous nodes, it's quite easy to see anomalies also in Euclidean, with the Euclidean distance. And so classical technique for that is the spectral embedding. So we'll talk about that. So it's based on the spectral decomposition of the Laplacian matrix, and it's very common. But here we'll focus on the physical interpretation of spectral embedding, taking different views, like in thermodynamics, mechanics, and electricity. So we'll play with that. So this is also known. What we've done mainly is to add dynamics to this system. So if you look at the literature, people consider static systems and will add dynamics. And this provides many, nice interpretation of the eigenvalues and eigenvectors of the Laplacian. But also it suggests an extension to the usual framework of graph embedding. And I won't say what is this extension. I hope that if I'm doing a good job, you will see what I mean by that, okay, during the talk. What is this extension that is not in the classical framework of graph embedding I've just talked about? Okay, any question?
Laplacian matrix.
So I will explain that. So the basic setting is the following. So I have a connected undirected graph, and there's no self-loops for simplicity. So A will be the adjacency matrix, a binary symmetric matrix with a zero diagonal. D will be the vector of degrees, and capital D will be the diagonal matrix of the degrees. We could add weights to this graph, in which case the weight should represent the strength of the link. So if you think of the flight data set, it would correspond to the number of daily flights between the airports. Okay, this is a measure of the strength of the link between these airports. So we'll just keep the same notation for simplicity. So A will still be the adjacency matrix, but a weighted adjacency matrix with positive entries, non-negative entries. And D will be the vector of the weighted degree, and capital D the diagonal matrix of weighted degrees. Okay. So this is the outline. So we'll start by walking at random in the graph. Okay, which is a good way to explore it. Then I will introduce the Laplacian matrix. The way to do this representation of the graph. And so I will talk about this extension I've just mentioned and some experiments. So random walk. So it's a natural random walk in the graph. Okay, so when you're at some node I, you will just move to node J with priority Pij, which is in proportion to the weight of the corresponding links. Okay, so it would be uniform if you have no weights. I mean, if weights are equal to 1. And so this defines a Markov chain with a transition matrix P. And so you can write the evolution of the distribution of the Markov chain. So pi t would be the row vector giving the distribution at time t. Okay, so the component I of this row vector would correspond to the probability that xt is in I at time t. Okay, so xt would be the state at time t. And so you're interested in general at the equilibrium, and so the equilibrium it's uniquely defined by this balance equation, where so pi is the stational distribution. It's a left eigenvector of p for the eigenvalue 1. So it's very classical, and you can check that the stational distribution is proportional to the degree of each node. Okay, so you will visit a node in proportion to its degree. And the convergence is at exponential rate, and the rate is precisely the second largest eigenvalue of p. Okay, so classical results. Now you can think of another random walk which is in continuous time. It's very similar, but it's not exactly the same. So in this case, you would move from I to j at a rate aij, which means after an exponential random variable with parameter aij. Okay, so the time is continuous now, and you can specify this Markov chain by its generator matrix, which is q a minus d. And so you can also write the time evolution of this Markov chain. So pi of t, now you get a differential equation. Pi of t is a distribution at t. And again, the equilibrium is just a left eigenvector of q, but for the eigenvalue 0. And it turns out that in this case, the stational distribution is uniform. Okay, because if you compare to a discrete time, so you will visit more frequently high degree nodes, but you move from them more quickly, okay, because you have more links. And the convergence is also at exponential rate, which is the second largest eigenvalue of q. So, I mean, some of you are probably familiar with that. So we'll see some connection with the physics I will introduce later. So the Laplacian matrix now. So it's defined by d minus a. So as you can see, is very close to the generator matrix of the continuous time Markov chain. This is minus q. Okay, if you remember, this generator matrix was a minus d. Okay, so it's minus q, and so it's a symmetric matrix because the graph is undirected, and it's also positive semi-definite. So you can easily check this equation. So u here is any vector, and so later we'll interpret that actually. Okay, in physics. But the mathematical consequence of this is that you can have a spectral decomposition of this matrix. You can write this as U lambda U transpose, where lambda is a diagonal matrix of eigenvalues, and U is the orthogonal matrix of eigenvectors. And a very important, a key remark is that here the eigenvalue 0 is simple. So it is an eigenvalue, 0 is an eigenvalue, it is simple. The only way to see that, the only way to make this equal to 0, which would be for the eigenvector for the eigenvalue 0, would be to have ui is equal to uv whenever I is connected to j. Okay, you need to set all these terms of the sum equal to 0. But since the graph is connected, this means that all u are equal, so which means that u is proportional to 1. Okay, so this is written here. There's just one eigenvector of the eigenvalue 0, and it is proportional to 1. Vector of 1s. Is this clear? Okay, so first interpretation, thermodynamics. So let's play with this following game. So you fix the temperature. Imagine you have your n nodes, and you fix the temperature of a selection of these nodes. Okay, at least 2. Okay, so you fix the temperature of these nodes, and you let the system evolve with the following interpretation of the weights. So the weight Aig would be the thermal conductivity of the link between I and G, which means this would define the level of heat exchanges between these two nodes. Okay, so if you do that, you can write the corresponding heat equation. If you look at any node outside this selection, so outside the boundary, the variation of the temperature would be equal to this sum corresponding to all the heat receives or given to its neighbors. Okay, and what is very nice is that if you can write this with respect to the Laplacian of the matrix. So it's minus LT, where L is a Laplacian. And actually, the term Laplacian comes from that. I mean, Laplacian is related to the heat equation. Okay, so if you look at the evolution, the solution of this heat equation, so at the equilibrium, then at the this is an example. It's just an example to get an idea of what happens. So here you have only 2 nodes with fixed temperature, a hot node and a cold node, and you let the system evolve, so you can, simulate this heat equation. So heat is diffused, and at some point you reach equilibrium. Okay, and the temperature, of course, of all nodes will be between the temperature of the cold node and that of the hot node. And so, if you look at the equilibriums, this is known as the Dirichlet problem. So you need to if you remember, this is a variation of the temperature of node I, for I not at the boundary. So you need to have this equal to 0. And equivalently, if you write in terms of the transition matrix of the discrete time random walk, it means that the temperature of each node will be equal to the average weighted by the weights of the graph of the temperature of its neighbor. Okay, it's very natural. So if you look at this particular node, so the temperature of this node will be the mean of the temperature of its neighbors, and the mean is weighted by the edge weight. Okay, so there's an interesting remark that if you consider a free system, so without any boundary, then the only the solution would be LT is equal to 0, which is the right eigenvector of L, which means just that the temperature of all nodes must be equal, which is natural. Okay, there's another interpretation which is in terms of mechanics. So in mechanics, you imagine that your points, so your nodes are linked by springs. Okay, so between any two nodes, you add a spring whose stiffness corresponds to the weight of the edge or strength. And what we will do is that we'll put all these nodes, so these point particles, let's say, on a line. Okay. So imagine there are plenty of whoa, wow. There are plenty of springs there. Okay, they are all linked by springs, but you put them on a line. Okay, and so you denote by V1, Vn, the location of these particles, and so Aij times the distance between I and j would be the force between them, and so if you look at the potential energy, this is given by this expression, which is exactly the expression I gave before. So this is a J, sorry. So this is a J. Cc, the one half times this is the potential energy of the spring, in the spring Ij. Okay? If you remember have you done some physics recently? Okay. And so you sum it, this is the potential energy. Now let's add dynamics. Okay. So, of course, you're interested in configurations where the potential energy is low. Okay. And one option would be, one trivial solution would be, let's put all nodes at the same place. Okay. There's no potential energy, and okay, you're done. But now, how to get the second, natural configuration of this system? Okay. How to find natural configuration, which is not a trivial one where all are at the same place. Well, there's a natural way to do that is to add dynamics, which means to let the system, for instance, rotate. Okay, so we fix the axis of this bar, and we let the system rotate. Okay, and so this will move the points. There will be an attractive force by the springs, and the inertia, or I don't know how you call it, the centripetal force, or I don't know. Yes?
Just a precision. I think it's not exactly a spring, because a spring you have a normal length, and it's difficult to get bigger or smaller. And here it's very costly to be small.
Oh, yeah.
So it's just a repulsive force, in fact, in your case, no? Yeah. Isn't it?
It's only attractive.
Or attractive.
It's only attractive.
Yeah. So it's
just
mass of low.
Oh yeah, it's a spring in a given regime. Well, let's say do that. Okay. Yeah. So you have energy only when you put a distance between the nodes. But I think it's a usual. Maybe these guys like me working on graph are not physicists and they don't know. But there's a spring layout, for instance, which is classical in many frameworks, and this is exactly what is meant. Okay, so we add this dynamics. We add, so you have to imagine this complex system with all these springs. There may be 1 million nodes. Okay, and you let the system rotate at constant speed, omega. Well, you have the Newton's second law of motion. So on the left you have the force applied to node I, and on the right you have the acceleration. It depends on the distance from the axis. And you have this very nice formula, which is that the configuration is just an eigenvalue problem, which means that there cannot be any angular velocity leading to this equilibrium. The square of the velocity must be an eigenvalue of the Laplacian. And the corresponding equilibrium is the eigenvector.
Otherwise?
Sorry?
So if you don't have
Otherwise, yeah, you can, well, I've not, I wanted to play with that, but of course you would have oscillations, no equilibrium. Of course, you can force the system in a different, not in one of these particular eigenmodes of the system, and then you don't have equilibrium. Okay.
But the solution will be reachable? I mean, even if it's a stable solution, maybe because you have no friction, it will still oscillate, even if...
Yeah, maybe you have to start from this configuration to have the equilibrium. I don't know exactly what would happen if you don't start from V. This is your question, I guess. Yeah.
So how's the graph attached to the rotating point? So I see it's
No,
rotating around one vertex.
No, they are just constrained to be on this bar. You may imagine there's no friction and they can cross over, so it's a strange system, but and that's it. They are not attached to the center. You may attach them. It's a form of regularization, but here there's no such connection to the axis. It's only through the bar, which is attached to the axis. Yes?
So it may happen that all the points, because you are rotating, are all on the...
Yeah, so
they go to infinity.
Yeah, but we look at equilibria.
Okay.
That's true, yeah, of course. Okay, so this is just what I've said. So you have only a finite set of possible values of angular velocity. You can have a look at the energy. So at equilibrium, so I've said just the V is an eigenvector of the Laplacian. And the potential energy is equal to the kinetic energy at equilibrium. And you can interpret, so if you replace V by its expression, you get this. And this is exactly the kinetic energy, because lambda is the square of the angular velocity. And V transpose V can be interpreted at the moment of inertia of the system. Okay? The square, sum of the square, the distance to the axis, provided all nodes have the same mass, which I've not mentioned, but they all have unit mass. Okay. So it's very interesting because this is something, why do you choose in practice? So we won't have a spectral embedding. We won't use all the eigenvectors. Okay, it's too large. There's 1 million. There could be 1 million eigenvector if your graph is very large, and you like to have a low dimension embedding, keeping, let's say, 10 or 100 eigenvectors. Okay, so when you do that, if you select, so typically you would select the first eigenvectors. You do that because that corresponds to the most meaningful configurations, those of lowest energy. Or lowest also velocity, okay, frequency. Well, it turns out that there's another way to introduce dynamics in this system. Do you have any idea? Okay, so I said people usually just consider a static system. Where is it? There. So one option is to let the bar rotate. There's another way to have introduce dynamics in the system.
Adding and removing nodes?
Yeah, they will move, but how?
Well, they will create links and...
Yes, actually, well, simply you just start from a given state, you choose on the bar, and you free the system, and you let all the nodes move. Okay. And if you do that, well, so you start from, so now the bar is fixed, and you choose an initial state, and you look at the equilibrium. Something may happen. Okay. And something happen precisely if you start from one of these eigenvectors. I mean, you have, if you look at so you can still write the Newton's equations, and you get exactly the same type of, so you get this equation describing the evolution of the state, of the location of this point. And you would look to periodic solutions. So equilibria here would mean periodic solutions. And you get the same equation. Okay. So it's another interpretation of these eigenvectors and eigenvalues. Okay. But it's like it's a periodic system. You can imagine that these nodes will fluctuate around the origin.
So you mean that you move a node and then this, let's say, disturbance propagates through the network because it creates other neighboring nodes?
Yeah. But in fact, so it will be something periodic only if you choose an initial state which is an eigenvector. Otherwise, something may happen, but it's not periodic.
You will have a sum of periodic solutions.
Yeah, something. Yeah, because you can decompose all of that. Okay, and you can again have the interpretation in terms of energy. So let's have a look at the Dirichlet problem now. So the equivalent of the Dirichlet problem would be to fix the position of some nodes and to see where the other stabilize. And so you can imagine that you have a nail here with your hammer. Okay, so this cannot move. It's like the heat equation. So you have the hot node and the cold node. You have the node on the right, the node on the left, and you let the system evolve, and you get exactly the same. If you look at the possible equilibrium of that, so the only possible equilibrium is a solution of the Dirichlet problem. Okay. And this solution actually corresponds to the minimum of the potential energy. Question on this mechanics? So the third interpretation would be electricity. Okay. I mentioned that also because it's quite standard. Some of you may know there's a famous paper by Snail and Doyle on the analogy between random walks and electricity. And because here, if you think of the system, electrons precisely move at random in the graph, and you have a direct connection between random walks and the physical system. So the classical interpretation is with a direct current, and so you replace each link by a conductor of resistance 1 over the strength. So if you have you have a strong connection between two nodes, I and J, which means that there's low resistance. Okay, the current can move quite easily between these two nodes. Okay, so you take the inverse of the strength of the links, and the now V1, Vn would be the electric potential. So you apply that, and the corresponding force, so now would be the current between I and G. By Ohm's law, the current from I to J would be Aij times the differential potential difference. And you get the power dissipation, which again can be written through the Laplacian. Is this okay?
We had a very old professor in Greece, and basically when we were doing networks, he was doing basically this type of thing.
Yeah,
this was the old-fashioned way to...
Yeah, but we'll see that this is very interesting, but a bit limited because it's very hard to add dynamics on that. So in fact, we'll have another way to interpret the Laplacian, which will be closer to the dynamic mechanical system, which will be, it consists in replacing the link between I and J by an inductor instead of a resistor. Okay, it's still 1 over Aij, So now between two nodes you have your inductor, and you add a capacitor between each node and the ground of unit capacitance. Okay? And if you remember this LC system, RLC, and so on, this typically has periodic solutions. Okay, you have these are electrical oscillators. And indeed, so if you denote by still V1, Vn, the electric potential of the nodes. So this is the potential energy stored in the capacitor. But the key point in that one is that if you start from some initial state and you let the system evolve, which is just the second interpretation of mechanics. Okay, you fix the initial state and then you let the system evolve. Here the same, you fix the potential of the nodes and you let the system evolve. And if you do that, you get, I mean, if you remember how an inductance and a capacitor work, you get these equations. Here I is the current between I and J. And you get, again, periodic solutions. And the frequency, the only possible frequencies of these electrical networks are the square root of the eigenvalues of the Laplacian. And you have an interpretation in terms of energy, which is slightly different, but let's keep that. And you have, again, the Dirichlet problem, but if you think of the Dirichlet problem, you will fix the potential of two nodes, so the best interpretation in terms of direct current, so now the links corresponds to resistors. And again, you can write the solution to the Dirichlet problem, and at equilibrium, the power dissipation is minimized, which is known as the Thomson principle. Okay. So here the color corresponds to the electric potential of these nodes. Okay, any questions so far? So what can we do with that? We can embed the graph, okay? And so we'll use, of course, the spectral decomposition of the Laplacian. But the embedding would be given by this. So it's more or less the eigenvectors. So U, remember, corresponds to the eigenvectors. So each column of U corresponds to an eigenvector. So each line or each row of U transpose would corresponds to an eigenvector. But the key point that you you normalize by the eigenvalues, and I will explain why. So the notation lambda plus, so it's a pseudo-inverse of a matrix, which means that this matrix is not invertible because there's a 0 at the first element. But you just invert what you can invert, basically. This is a pseudo-inverse. Okay. Well, and so if you look at this embedding, so each node will be represented by a vector here in dimension n, just because I've kept all the eigenvectors. Of course, what we will do in practice is that we will truncate this. We'll keep the first 10 we'll truncate here. So we'll take only the first eigenvector. So if you look at what happens, so ut, if you look at ut, so x1, xn, so this is the matrix A, it will be equal up to normalization to u1, u2, un. So u1, un are the eigenvectors, okay? And so it means that the first coordinate would correspond, of each node, would correspond to the first eigenvector. The second coordinate for each node would correspond to the second eigenvector, and so on. And if you like to truncate, you just keep the first k eigenvectors if you'd like to have a low dimension representation. Okay? Basically, this is what happens. The only trick is that will normalize by this inverse of square root of this eigenvalues. So here it would be 0 because we cannot do anything. So basically, the first coordinate would be 0 for all nodes. Then 1 over square root of lambda 2, and so on. Why do we do that? Because in doing so, we'll equalize the levels of energy of each coordinate. Okay, if you look at the potential energy, it's V transpose LV, which is lambda V transpose V. And if you normalize by 1 over square root of lambda, you get an equal energy. Okay, so it's a physical interpretation of this normalization. And the last comment is that the center of mass is at the origin. Okay, we'll see why it matters. Okay, so this is what you get, for instance. Of course, I've just skipped the first coordinate, it's 0. So these are the second and third coordinate of this graph. So you can imagine that on the up to this normalization factor, on this x-axis, you get the equilibrium at the lowest. If you think of the mechanical system, for instance, you let the system rotate at the lowest speed, and you get this vector. Yes?
So, about the embedding, usually if you want, for example, to map from a higher dimension to a smaller dimension, you would use something like principal component analysis, right?
Yeah.
So in the principal component analysis, you would have also a diagonal graph.
Yeah.
Which is also symmetric, because basically it comes from A times A transpose of what you want. And so this will have real eigenvalues, and you will take the square root of them.
These are real as well.
Yes, exactly. So
Yeah.
I'm trying to understand what would be the difference of what you're doing with the principal component analysis.
So there will be actually a talk on that by Nathan. It's related to the SVD of the Laplacian. So it's very similar, but you don't have this physical interpretation. Okay. And the random walk is not the same. But you're right. This is another way to embed the graph.
Right, because it is the SVD basically what...
No, it's not SVD.
No, but if you take the SVD, it's the square root of your eigenvalue.
Yeah. So if you take the SVD, it would correspond exactly to the...
So I'm trying to understand what would be the difference between the two.
No, but the singular vector are not the eigenvectors.
Yes, exactly.
So it's not the same embedding.
So what is the difference? That's the question.
Yeah, so Nathan will address that. Okay, so that's not the end of the story. So there's a very nice... So as you see, it looks good. I mean, here you have nodes that are close, that are strongly connected. They are together in this embedding space. So can we interpret something like the distance between two? What is the distance between two nodes? Is there a physical interpretation of that, for instance? The answer is yes. And the square distance between I and j corresponds to the inverse of the force when you fix the distance between these two nodes in the mechanical system. So if you think of the Dirichlet problem, so you fix the I at 1, j at 0, so things organize, okay? And at the end, you look at the force between I and j. Okay, so the inverse of this force is a square distance. If a strong force, then they will be close in the embedding space. In terms of electricity, it corresponds to the effective resistance. If you remember your calculation of effective resistance, it's exactly that. And in terms of random walk, it is the mean commute time between I and j. So you start from I, you wait having reached node j, you come back to I. And you look at how much time it takes for this round trip. And this is the square up to a constant corresponds to the square distance between I and j in the embedding space. So the longer it takes, the more distance are the nodes in the embedding space. No?
I was thinking about the symmetry between computation time between I and j and I.
So it's a commute time, so it's completely symmetric.
Okay, but yes.
But it's true that the heating time of j from I is not symmetric. There's another interpretation of the distance from the origin of each node. So you don't take a pair, you take each node individually, and you look at how far it is from the origin. And again, it would correspond to the inverse of the force, but it's a bit more tricky. It would be the force exerted on I in the mechanical system when I is at distance 1 from the center of mass. So basically, you replace J by the center of mass of the system. Okay. For the electrical system, you replace J by the ground. And you look at the effective resistance. And in terms of random walk, it corresponds to the mean heating time of A from steady state. So anyone, you start from just the average from the stationary distribution. And this is also interesting metric. If you like to do some clustering, for instance, or you'd like to know what is the similarity between I and J, you could use what is known as the cosine similarity you may have heard about. So you can express so this is really the cosinus between the two vectors, which you can express this way. And it's a sort of a normalized measure of the inverse of the force, of the commute time, and so on. And in practice, it's much. So basically, what you compare is so you do not simply compare I and J through, let's say, the mean commute time. This is the mean commute time in the random walk. You compare this to how long it takes to reach I and J separately. And in practice, it's much more efficient than just using the Euclidean distance. And I will show a couple of experiments where you can at least see why the angle makes sense. There's another way to embed the graph, which is through the normalized Laplacian. So it looks similar. It's just that you normalize by D. So and you make this symmetric. So if you remember, this is P, the transition matrix in discrete time. So it's very similar to so it's related to the random walk in discrete time. And you have the same type of results and so on. And you can use that to embed the graph in the same way. But that's it. I cannot give you any physical interpretation of that. And people, use one or the other Laplacian. They do not motivate that. It's usually, well, it works. And that's it. Okay? So half of the paper use a regular Laplacian, half the paper use a normalized Laplacian, but they don't really motivate that. So what is missing?
An extension.
Yes. So how to interpret this embedding? Let's try to see. Well, we'll assign additional parameters, which are the weights of the nodes. Okay? And these weights would correspond to the relative importance of each node. Okay? So it would correspond to the value you attribute to each data. It would correspond to the reliability of your data. It may correspond to its multiplicity if you think that each node is a category representing a population of items or whatever. Actually, it's very usual for vector data. People, if you think of k-means, there are versions with weights applied to the nodes. But it's really not applied to graph data. And that's what we'll do. And so, actually, so we'll extend the framework, and what we'll see is that if you take unit weights, so all nodes having the same importance, you get the regular Laplacian. And if you take the vector of degrees, you get the normalized Laplacian. Okay, so now, what would be the physical interpretation of these weights or masses? Yes. So this is a weighted Laplacian. So you have an external parameter which is W, the vector of weight. And so you can check that if W is equal to 1, big W, capital W would be identity, this is regular Laplacian. If it's D, it's a normalized Laplacian. And you can do the same type of embedding. And now you can interpret everything. The weighted Laplacian and its spectral decomposition can be interpreted as physical systems where the weights would correspond to the heat capacities of each node in terms of thermodynamics, the masses in mechanics, and the capacitances in electricity. And of course, actually, I had decided just because I wondered why are these. I first came with this mechanical system. I let it rotate, and I asked myself, why are these masses all equal? I mean, okay, that's a choice, but you can choose whatever you want. You have the corresponding random walk. We'll skip that, and you have an embedding, okay, which is very similar. And the center of mass now is you account for the weights of each node. And now you have this physical interpretation of the distances in the embedding space, which corresponds to the inverse of the force, the effective resistance, of the mean commute time of this weighted random walk. Question? Yes?
So my question is basically, you have created, you have already a graph that connects nodes to one another.
Yeah.
But you consider that there are additional weights,
yeah.
labels,
yeah.
that have nothing to do with the
yeah.
connection.
Exactly.
Is this a hypothesis that will always hold, or because sometimes?
No, it gives you an additional level of freedom. I mean, if you have the information, then it's good. You can incorporate it in the embedding. If you don't have it, there are two natural options, which are uniform weights or degrees, and that's it.
So basically, you believe that there's no correlation basically between the labels and the graph?
They could, I mean, in your data. You assume that you have the information. Okay. And the point is that you can really embed the graph using that. So, but actually, the answer is no. But what is the question? For further question. No, there's a key question there. Think of the impact of the weight. Think of the mechanical system.
If there is always a...
Think of the mechanical system. You put I. So you put I. This is a nail. Okay. I is there. J is there. Cannot move. Then you have all the others. There are springs and so on. And you look at the equilibrium. At equilibrium, the force between I and J is related to the distance between I and J in the embedding space. So the answer is no, but what is the question?
Does it depend on their mass?
It does not depend on the mass. Does it depend on the mass? No. The answer is no. So actually, the embedding is the same. So, it was quite intriguing because if you think of the random walk, the commute time does not depend on the weights as well. This was quite surprising. This was a remark of Mark, and we discussed, we have exchanges to understand that. So it does not depend on the weight. So the weights do not change the geometry of the embedding. So it's completely useless, right? Why having done everything? Actually, what you can prove precisely is that weighting just corresponds to a shift to the center of mass. Okay, so Z here is the regular embedding shifted to the center of mass. Maybe the center of mass is not there because it's not at the origin because of the rate. And so it's not exactly, there is some rotation that is possible, but the geometry is exactly the same. So the geometry of the weighted embedding is the same as that of the regular embedding shifted to the center of mass.
And it remains true when you have more than 2 fixed mass?
Yes, because, the solutions to the Dirichlet problem does not depend on the mass. It's not a dynamic system. So why?
Is it the same truncations?
Sorry?
Is it the same truncations?
No, of course. It completely changes the first eigenvectors. It changes the levels of energy. So when you truncate, it's completely different. This is why it's important and this is why the normalized Laplacian, the regular Laplacian, give completely different results. Okay. So the weighted spectral embedding is given by the equilibrium of lowest energy. And so the truncation, of course, here the masses or the weights matter. But if you can afford having, all eigenvectors, the maximal dimension, then it does not, just a shift. Well, a few experiments just to see what happens. So this is an experiment on Wikipedia for School. It's a small subset of Wikipedia with a few thousand nodes. And so we make the graph undirected and unweighted. Okay. So there's a link between I and j if either there's a link in Wikipedia from I to j or from j to I. And we show the impact of the Laplacian on the embedding. This is what you get for the regular Laplacian, the normalized Laplacian. For the spectral embedding in dimension 50. And after normalization, which corresponds to applying cosine similarity instead of Euclidean distance. And so to see what happens, I've applied a Tisny visualization. Well, you see that the embeddings are quite different, and indeed it looks better on the right. Here you have mix of these are categories. So it's a subset of the pages. So blue corresponds to arts, literature, mathematics for green, physics, countries, and mammals. And there's a mix of blue, so arts, literature, and country there. Well, it makes sense, but it looks like it's much better clustered in the normalized Laplacian, with some. You have some books, let's say, or writers connected to the countries, which may make sense. Okay. And it looks better, but it's only qualitative. We can have a quantitative result. So what I've done is I've measured the average cosine similarity. So you take all. So this is for the graph. So it's average on the graph. So you take all pairs ij, all links in the graph, and you look at their cosine similarity, and you take the average. Okay, and you'd like to compare this to something else, and this something else is just all pairs. So you expect the first term to be larger than the second. Okay, and so the first one is something between 0 and 1. This is between 0 and 1. Actually, well, you can show that this is positive. And actually, you need something to compute that, okay, because the complexity is in n square here. But of course, you can write this as a scalar product, and you take the sum, so it can be written at the square norm of z being this vector. So the computation is linear in n, and this term is positive. So this measure cannot exceed 1. 1 would be the best possible embedding with all nodes linked by an edge being the same, having the maximum similarity, and 2 random nodes having a 0 cosine similarity. And this is what you get for the regular Laplacian and the normalized Laplacian. So you get the first term and the second term. So if you look only at the first term, it looks like the regular Laplacian is better. But actually, this is because all nodes are concentrated on the same place. The cosine similarity between any 2 nodes is also very close to 1. So you don't use all your embedding space. If you look at the normalized Laplacian, so the first term is lower, but you have almost 0 cosine similarity between any 2 nodes. So the difference is much better on the normalized Laplacian. And it makes sense because if you think of the mechanical interpretation, the big nodes, you may think that Wikipedia or these sort of graphs are organized around these big nodes. And so if you have the lowest levels of energy, you have well positioned your big nodes, then you get meaningful configurations. Okay. If all nodes have the same weights, you may, you may get more noise in your embedding. Okay, that's it. So you can get useful insight from the physics and interpret this spectral, so the spectral properties of the Laplacians. You can naturally extend this framework to account for node weights. And now if you like to choose one Laplacian or the other, if you don't have these weights, well, you can argue that this is as if you consider that the weights of the nodes are equal or are proportional to the degrees. Okay, and this would correspond to a random wall in continuous time or in discrete time. That's it. Any question or comment?
Yes. So when I was doing physics when I was a little boy, the professor told us that for some problems, if you have a mass m1 at position x1 and a mass m2 at position x2, you can sometimes replace these two masses by an equivalent mass m1 plus m2 at the barycenter and make all the computations remain the same in the global system. So here I'm wondering if I cluster my nodes in the graph and replace formally by an equivalent node with the total mass of all within the cluster. Does the physics remain the same? Or
I guess so. It needs to be written, but I guess so.
I guess that it would be in the case where you have nodes that are clones of each other, in the sense that they have exactly the same edges, the same links to nodes outside your set of clones. You see what I mean? So if you have 2 nodes and they have exactly the same weight to external nodes, then you can merge them, I guess. Otherwise, there is no easy way to do that.
okay.
See what I mean?
Yes. That it reminds me something that there's actually with these weights. I mean, it's related to what you're saying. If you're interested in some part of the nodes, let's say these are the nodes you are interested in. Well, an option would be to consider only the subgraph, but you would lose a lot of information if you do that. But you could consider the equivalent. I mean, you could consider the equivalent system, so equivalent mass or spring strengths between this node and so on. And if you do that and you apply the center of mass here, so the center of mass would be there, you would see that the angular, the cosine similarity will allow you to distinguish between different sub-part of this subgraph, which you would not see if you let this center of mass there. So well, maybe it's related to, I don't know if it's really related to a question, but it's a comment that these weights allow you to look at, to focus on a part of the graph.
Yeah, if you shift, like the commute time doesn't change, but the cosine changes.
Yeah. But, and there's a notion of not equivalent mass, but equivalent strengths or resistors.
One example where the normalized Laplacian was better than the Laplacian, is that generally true? Is it now necessary to always use the normalized Laplacian?
Well, I think it's strongly related to the power law of you observe in graphs, in real graphs, so that.
The answer is it depends.
Yeah. You've looked some.
But the thing is, for large graphs, when you want to extract eigenvalues of the Laplacian, you have to use like our methods, and usually the normalized Laplacian is better conditioned for this kind of iterative methods than the standard Laplacians. But in terms of quality of embedding, I have examples. Sometimes the normal, regular Laplacian is better.
But well, my interpretation is that it's more stable, and it's a physical interpretation because you have a power law in real graphs, so things will organize around these big nodes. And maybe it's related to what you say. Calculating, I mean, these eigenvectors is easier, and it's more stable and so on. But also, you may think that things are organized around these big nodes. And it makes sense to give these nodes a higher weight. If you look at the Wikipedia pages, there are pages no one knows about them. And if you give them the same weight as pages like Einstein or I don't know, maybe it's not really what you look for. Yes.
I think there is a fifth interpretation in terms of harmonics with chords or something like this.
Yes. Good.
I'm not sure.
So
if you consider a guitar, for example, I think there are some interpretation with
good.
eigenvalue and,
So you.
But it's a continuous graph if you want.
Okay.
So if you imagine an infinite graph where atoms have the element of graphs, something like that, and you compute the Laplacian of that,
Yeah.
it gives you the sound.
It's like the usual heat equation is in continuous space.
Yes, exactly.
But here the point that it's discrete. I mean, it's really something important. So I don't know what would be the chords. Maybe I don't know. It's clear that the Laplacian is everywhere in physics. Yes.
One question about the metric of distance that you use.
Yes.
Basically, like the cosinus.
Yes.
From the expression, I think this is basically based on the definition. It's a definition of cosinus. What you give,
Yes.
right?
Yeah.
You just write cosinus from the left-hand side.
Yeah.
So basically, this describes only the angle. However, if we see this two-dimensional embedding, it's not only the angle, but it's also the distance that changed between the two Laplacians that you gave, especially in the Wikipedia example, I think. that there were also different distances between the nodes.
You mean in two Laplacians?
Yeah, nodes.
Using the two Laplacians?
Yes, you gave the
Yeah, because you
example.
have truncated.
Right.
Yeah.
So in this sense, the angle will not be a sufficient description, right, of your embedding, because, right, so you will have different distances also. So imagine, for example, that if the angle describes well the position of the nodes, but for the one example, the nodes are very close to each other, so you cannot really distinguish them. On the other, they are much further, but the cosine symmetric would be better.
Well, it turns out that if you look at these embeddings, it's really
The other example of the Wikipedia.
it's very classical to have these directions. Like, well, of course, it's only in dimension 2, but here the cosine similarity would be much better to cluster these nodes.
Yeah, but if they were closer to each other, the cosine similarity would be the same. This is what I'm asking. Even if all the nodes were more closely in the center.
Yes, and?
So I'm asking, like, would this be sufficient to separate them? Like, because there, for example, you have different color for different categories.
Well, so I don't have any theoretical or I mean, argument to say that cosine similarity is better than the usual Euclidean distance.
Is there anything that combines the two, or that would work better?
Well, in a sense, if you look at cosine similarity, you combine both. Just a normalized measure, as I said. As I said, instead of just comparing square distance individually between them, you take a normalized measure.
But no, because basically this thing is that imagine that you have x1 minus xi minus j squared. What is equal? Xy minus xj squared is equal to xi squared plus xj squared minus 2 times xi xj cosinus xi xj. So basically it's just the definition of the distance of points. So essentially this is just the angle. So,
yes.
But this doesn't have the relative distance between the two.
No.
So I'm asking if there could be any other, like...
Well, you mean combining cosine similarity with distance, for instance?
Yeah.
Well, why not?
Would it bring something? That's my question.
I don't know. You have to choose something, a metric. So in practice, I mean, we are working on that with Nathan in particular. If you compare cosine similarity to the usual Euclidean distance on real graph, I mean, the difference is amazing.
Yes, exactly. It's a different thing, yes.
But it's much better to take the cosine similarity. Really, so we cannot really say why, beyond the fact that it's a normalized measure. Okay, thank you.